afternoon's section of the symposium honoring Heinz Heinemann. Our first speaker, as you can see from the slide, will be Enrique Iglesia from the University of California, Berkeley. Enrique will be telling us about some of his experiences in working with Heinz, and I think he'll have some pictures and so forth. Of course, Enrique is known very well to everyone here, and I'll just mention that he is also the most recent podium lecturer at Northwestern University. It's our pleasure to have Enrique come and visit us several times over the last year and a half. So, Enrique, we'll look forward to your presentation.
Good afternoon. It is an honor and a pleasure to be here today to celebrate the life and the accomplishments of our good friend Heinz Heinemann. I have to admit that I came into Heinz's life quite late. It was my loss to have come at the point where I could no longer participate in sort of the heady days of catalysis, where all the scientists were handsome and well dressed. I was actually in first grade at the time, and I was seriously considering the catalysis career, and of course Heinz at the time was already setting the groundwork that I would follow, and I decided to go into catalysis in no small part because of the example that was set not only by Heinz, who was a leader in this area, but also by some of the pioneers that I am still in awe of. These are the people that we have tried to imitate over the years, the ones that we remember, and the ones that, whether they're here or not, still sort of set the way for the rest of us to follow. One of the last times that I saw Heinz, and probably his last really public appearance in this kind of a meeting, was at the Philadelphia meeting 2 years ago, where Henrik and I got to celebrate our respective awards, and where Heinz was one of the guests of honor at that get-together. And I remember quite vividly because there was a picture that was taken, and my son, who attended this for the first time, he's not a catalysis person, described this as the catalysis Woodstock. And I guess this is some of the old stars and some of the, I hope, soon-to-be new stars in the area. And I also remember it quite vividly because I came up to Heinz after his presentation, his spellbinding presentation in the evening. I remember that everybody was standing up. This is right after his talk at the dinner. Everybody was standing up, and then afterwards there was a line of people looking for his autograph. And I remember coming up to him and saying, Heinz is the rock star of catalysis. And of course, I didn't know at the time that Heinz was not a fan of rock and roll or anything like that. And I don't think he took it the way I intended it. I never got a chance to really tell him what I really meant. And that is that I didn't know anybody else in the area whose autographs were as highly sought as his were after this meeting. So again, I stand here doing what I think I know how to do best in memory of Heinz, which is to tell you about technical work. And I think he would have been happy to hear, because he was one of the people who was instrumental at a very stressful time in my life when I was starting a new career to sort of give me the advice that ultimately I ended up following. Not only did he give me the advice, he also gave me quite a bit of his knowledge and quite a bit of his equipment and quite a bit of his laboratory space. And therefore, I have chosen to talk today about membrane reactors because that was the specific direct legacy that I got from Heinz Heinemann. This was a project that he started and he never got a chance to finish. He said it's going to take too long to do it. Little did he know that it was going to take this long. I'm going to give you what is a temporary progress report in an area that has been so difficult that I'm not always encouraged to proceed, but I'm going to tell you what we know and how we got there. He was very interested in methane conversion. And of course, one of the areas that you will hear about during this meeting is what is it that we should be doing with methane. And what we should be doing is, among other things, converting it to products that normally come from other sources, whether it be hydrocarbons, petroleum, or coal. There's a way to do this that goes directly. And there's a way to do this that goes indirectly. And when you go indirectly, you go through this, which we call syngas, and then you convert it to other products. This was a time and place where the area of direct conversion was actually quite popular, quite interesting, and we were all very excited about. And this was an area that Heinz began to work on, and then towards the end of his career, ended up working with David Ginter in trying to begin this project, which I'm going to tell you something about. This is the specific direct conversion that was so difficult that just to put the reactants in there and ask them to convert to what you wanted was not possible. And therefore, there would have to be some clever ways of going around what is almost an intrinsic hurdle in the chemistry that keeps you from doing very well. What you want to make is molecules of use, and thermodynamics and dynamics and chemical kinetics usually get in the way. So let me introduce the subject first by saying that if you bring methane to a surface and it breaks apart, what you hope is that when they come back together, they give you something useful. And that something useful, for example, would be a molecule that already has a carbon-carbon bond. However, in order to make this molecule, you need to go against thermodynamic tendencies that say this is not what you should make. This is a reaction for which not only do you need to bring energy, but where the Gibbs free energy is very positive, and therefore it works at only very high temperatures. Whether you want to make a C2 or benzene, for example, you have something that catalysis cannot do something about, which is to overcome thermodynamics. So the unfavorable thermodynamics led people to say, well, look what you're doing here. You're making hydrogen. Why don't you take the hydrogen and in some clever way make water? We all know what happens when we burn hydrogen with oxygen. It goes poof, right? And when it does that, it generates the energy and the free energy that you need in order to make the products that you want. And in the process of doing that, we have brought an oxidant into that chemistry, and we're asking it to do something that is rather selective. We're asking it to go after the hydrogen and not to touch the rest of the molecule. This is what we want to do. And we want to do it in the presence of oxygen. But of course, when you have oxygen around, you have a thermodynamic endpoint that usually is not a C2 molecule, but it is CO and CO2. And of course, this is what we call oxidative coupling, or oxidative conversion of methane. And it does provide a significant thermodynamic incentive. It avoids the problem of the non-oxidative routes, but now you've created a problem. How do you convince a molecule to do this, but not to do this? And that is, of course, one of the challenges. So one way to address the challenge, and these are the discussions and the beginnings of a project that Heinz had at the time, was why don't we take the oxygen back out? Actually, don't take it out, because then you're back at the beginning again. What you want to do is you want to put it on the other side. On the other side of what? On the other side of something that doesn't let anything but the hydrogen go through, so that you don't have to play with selectivity anymore. The selectivity is imposed by a barrier that gives the oxygen access only to the hydrogen and not to the rest of the molecule. And of course, the way that we're going to try to do that is by going back, taking the oxygen out, and trying to do what normally goes by the name of pyrolysis. And if we do pyrolysis, we can do this. The hydrogen, of course, is being produced and the thermodynamics are unfavorable, and you also have a problem in that this usually goes to very ugly molecules that, for lack of a better name, we call C-star. That means carbon, that means things that are not very useful. The way that we try to get around that problem, and this brings me back to one of the materials that was always dear to Heinz, and I used to refer to it as the magical material. It worked for everything that we ever tried. It doesn't quite work for doing this, and it doesn't work unless we modify it in some way. But the objective here is to now use catalysis rather than the thermodynamic problem, and to keep this from going all the way to carbon, to growing too far. And of course, small channels in zeolites tend to do that rather well. These materials were become known at the time, and we ended up with sort of a good part of a career looking at how to make and how to characterize those materials. Finally, what Heinz had in mind was, of course, to separate the non-oxidative part of the chemistry, to take the hydrogen across a selective membrane, and then to, if necessary, extract it or burn it on the other side. And in doing so, you can have the stoichiometry of an oxidative reaction without the oxygen and the carbon part of the hydrocarbon seeing each other. This, of course, is no easy task. And as a result of it, we took a fairly systematic approach that again began while Heinz was still at Berkeley and continued with his advice over many years. It took many, many years as he had predicted, and it took much longer than at that time he wanted to dedicate. So as the young child coming into the world at the time, he said, you have the time to do it. And we spent the next 10 years trying to make it happen. Well, the systematic approach was to ask the question, what do you really need in order to be able to do this? And this takes us into chemical reaction engineering and how do you go about describing membrane reactors. And we did that. I'm going to tell you some of the highlights of what we did. Then we had to make a membrane that was sufficiently stable at high temperature and had the right flux in order to be able to transfer the hydrogen without it itself dying as a result of that operation. Then we needed to get catalysts that had the right reactivity, the right selectivity, that would not deactivate very quickly, and then we had to put it all together into something that looked like a membrane reactor in the academic sense of that particular word. I'm going to take you through a brief tour of what this looked like. There will be very few equations that you don't need to remember, but we sort of paint a picture of a tube. You're bringing methane in, you're coming with something at the back end, there's hydrogen that is being generated, and you need to know how fast this is going to happen inside that tube. The next thing that you need to do is you need to know how one part of the tube communicates with the other one, and effectively that is now in the realm of reactors. Do they mix, do they not mix, is it dispersed or not? Okay. And then you sort of follow along this reactor to see what happens. And then you need to put a leak at the wall in order to be able to extract the hydrogen, and you need to figure out what sort of leak rate do you need so that you balance the rate at which you make the hydrogen with the rate at which you remove the hydrogen. This is all equations at this point. There are numbers that go with the equations. There are simulations that go with the equations that effectively say what happens if you don't have a catalyst. You can do this in the gas phase. We do it all the time. That's how steam crackers actually work, okay? But if you do it in the gas phase and you have all the kinetics and all the dynamics in this reactor, you get this beautiful plots which don't mean anything to you at this point. This is the amount of methane that is converted. This is the yield of the product that you want. And you have two axes here. This measures in this direction how good the membrane is, how fast you're removing hydrogen. This measures how long you leave it inside that reactor. What it tells you is that if you're fortunate enough, you can get yourself up here at that point, and that will give you about 90% yields of the products that you want. The problem, however, is that if you look at what it would take as far as time inside a reactor, and what it would take as far as the transfer rate in a membrane, you find out that it will take you 40 hours inside that reactor in order to get to that point. However, you will be able to use a very thick membrane. This will never work, but we knew how to make the membranes, and we knew that there was gas-phase chemistry, but it was not practical. So what we had to do was we had to figure out what was practical. And what was practical was something that would give you the right conversion in a given residence time. That's what this axis means. And it would have the right amount of hydrogen coming out of that reactor in order to be able to do it. In fact, what this tells you is that if you park yourself at a reasonable residence time in a reactor of about 2 minutes, and if you park yourself at a given value of that membrane property that gives you that yield of product, you effectively have a 10 to 100 micron membrane. This will work. We need a catalyst and we need a membrane in order to do it, and now that is the next challenge, but at least we know what we need. We need a catalyst that is active enough to do it in 2 minutes, and a membrane that is thin enough to be able to do that. And of course, that's what took the 10 years after that. Okay. So now, as far as the membranes are concerned, and these are things that were already going on at the time that I joined the project, we began by trying to make very thin films of materials that were stable at these severe conditions where this chemistry takes place. And that meant no palladium, that meant no porous membranes. That meant something that was a solid and could diffuse only hydrogen through it, and that took us to ceramic membranes. The first thing that you need for a ceramic membrane is a way of supporting them, because otherwise they break apart. So you have to get a porous substrate that was sufficiently mechanically strong and sufficiently permeable to be able to support a thin film, and then that would not fall apart as you go through any sort of temperature cycling. Not only could the support not fall apart, the thin film could not fall apart. And that meant that you had to match the properties of the support and the film so that the two of them will expand and contract at the same rate. I am not going to tell you that we figured out how to do this by any sort of systematic intellectual effort. I mean, this, as most of the things that we don't quite understand, came from trying and learning and being alert. Some of the things that, again, Heinz told us many years ago we needed to do. Okay? And in fact, in this case, it was his guidance in the early stages that convinced me that this methodical approach of mine that said I had to understand things before I went in the lab and tried was not going to work in this case. And indeed, he was absolutely right. But at the end of the exercise, we made beautiful films that stand to this day as sort of the state-of-the-art in hydrogen permeation. These materials are perovskite-type structures. They conduct hydrogen as protons and electrons as electrons, so that you actually do not have to apply a voltage and you do not have to short-circuit the two sides. These materials form films that were anywhere from 10 to 100 microns on a porous substrate that was stable under the hydrogen conditions on the other side, and whose surface, at least at first sight, appeared to be free of any pinholes. In fact, they were extremely stable against any sort of cycling, and they were able to operate in a membrane reactor in which we brought hydrogen across. How do we know how good they are? We know how good they are by measuring how fast they actually permeate hydrogen. This is a palladium metal membrane, 20 microns at its highest possible temperature. I need to operate them at much higher temperatures because of the methane chemistry that I'm trying to do, and these materials have similar permeation rates, and therefore were useful. The next step in this process was to actually try to make a catalyst that would be able to, again, stand the use in these kinds of reactors at the same time as we were removing the hydrogen. And we did that by going back to materials that we had been working on, and Heinz had began to tell us about a while back, in which we actually attempt to do this in the presence of a shape-selective zeolite. A zeolite that, again, keeps the formation of large polynuclear aromatics from destroying your catalyst. Again, remember, it is thermodynamically unfavorable, and therefore it will only go up to a certain point. And after that, it will stop going, because you will have enough hydrogen in the system that you will not be able to make any more of the products that you want. And again, this is the significant problem. The materials, as I mentioned earlier, are materials in which you have the CSM5 structure with 10-member ring zeolites, within which we managed to exchange a cation that ultimately became the active site for this chemistry. We talked quite a bit over the years about how these materials are made. And this materials is what I call the accidental catalyst, because it was made by mistake the first time, and it is made by accident every time thereafter. Nobody has ever been able to put a molybdenum oxo species inside a 10-member ring zeolite by going and doing what we call exchange. What happens is you put it on the outside as molybdenum oxide, and then we mindless go and heat the catalyst up, and of course, molybdenum oxide is volatile, and as a result of it, it finds its place in the gas phase to where we wanted to put it all along. It turns out that it makes materials that are beautifully composed of dimer-type structures, and they do this not because we're clever at doing it. It does it because that's what thermodynamically they want to do if you put them in the gas phase. But this is not the catalyst for the reaction. As Professor Lunsford showed many years ago, what ends up being the catalyst for the reaction is actually a carburized version of this material that then activates methane within a constrained environment. And what do you do next? You make C2 molecules, and what do the C2 molecules do? They do and go to an acid site by the same mechanism that Heinz taught us many years ago, the bifunctional mechanism by which you actually do metal acid chemistry in order to build high molecular weight hydrocarbons and rearrange them. And in fact, the mechanism for the reaction is one that involves the formation of olefins, the reaction of olefins on the acid sites of those materials in this bifunctional scheme that eventually builds the more stable molecule of toluene. We can change the amount of molybdenum and we increase the conversion of methane. Of course, that's not really what is all that critical, but we also get significant selectivity to benzene and yields that are actually limited by thermodynamics in the case of C2 to C10 hydrocarbons. Okay, now we need to put it inside a membrane, and this will bring me to the end. And probably the most difficult part in sort of a non-scientific way is how do you put together a catalyst and a membrane, not in a large-scale tubular reactor because we don't know how to make them in those systems, but in a system where you have to seal, you have to make sure that things do not thermally cycle, and so on. We need to put it in a place where we can get the hydrogen to go across and then bring some in on the other side in order to make it happen. And this brings us to the catalytic membrane reactor, which is, again, the academic version of how do you prove a concept. How do you decide whether it's worth going to a larger scale system and see whether it will work or not? Well, this was sort of the contraption that we ended up building, and this was some of the, what I would call the intellectual debris of the things that never worked too well, and that is that we taught ourselves quite a bit about things that we never intended to learn about. The students benefited from the experience, regardless of whether this will ever work or not. And in fact, I'm lowering your expectations right now to make sure that you don't expect the next one to have the 90% yield. What I'm saying is that we took a systematic approach and there were some things we learned. How to build membrane reactors, how to build thin films, how to put them together in a way that would allow us to explore a concept that Heinz had first thought about well before I got to Berkeley. Well, this is what the chemistry looks like. This is the yield of benzene. This is a fairly high temperature, about 720 degrees Celsius. The catalyst activates during the reaction, and then at this particular conditions, it reaches its thermodynamic limit. At this point, this catalyst does not have a membrane removing the hydrogen. What do you expect? If I turn on the membrane, if I actually put a membrane in at that point, I expect to be able to pull a certain amount of hydrogen. And when I do that, there should be a new thermodynamic endpoint. That new thermodynamic endpoint was achieved in this particular experiment. Of course, no one gets very excited about going from 4 to 6, but it proved the concept. However, there was a series of problems that this rather crowded slide that I could not break into a simpler form, okay, actually shows. And that is that this is effectively, in this case, is the conversion of methane for a separate experiment, in which we did the experiment with a conventional reactor, and we did the experiment with a membrane reactor. And of course, the conversion is higher. But two things are unhappy. One of them is that it is higher at the expense of things that you do not want. What happens when you pull hydrogen off from the system is it doesn't stop at benzene, it doesn't stop at naphthalene. It does what we taught molecules to do when you remove the hydrogen, which is lose more hydrogen. And as a result of it, you end up making a product slate that is not what you wanted and not what the simulations told you that you would have. The other one is that the catalyst begin to deactivate even more rapidly than with the removal of hydrogen. Of course, the reason for that is the same one. Those molecules you don't want are the ones that are keeping the active sites from being accessible. We learned how to put other molecules in there. Specifically, we discovered that CO2 is able to bring down the amount of products that you don't want. It allows you to increase slightly the amount of products that you do want, and it stabilizes the catalyst against deactivation. This is one of the reasons why it took 10 years, because we didn't give up at this point. We kept trying in order to make it better, but at some point in this exercise, we have reached another intellectual barrier, and that is that you can remove all the hydrogen you want, but the chemistry is not particularly happy when you do that, even if you are trying to do all the right things in order to get that to happen. This is a summary slide. I'm mostly done with the technical remarks. This is what I would call the intellectual debris. These are the things that we learn as a result of doing things methodically, systematically, trying to learn as we went along. This is what we learned as a result of the things that did not work as well as we expected. We learned how to make things that went well beyond the molybdenum ZSM5 that we started off with. And we developed a whole group of techniques to characterize and to make materials that could not be made by anything but sublimation methods. We learned how to make thin films, okay, and we taught other people how to do it even though we're not doing it in my group anymore, and how to support them on things that were mechanically strong. And finally, we had a small improvement in practical conversions and yields that was greatly outnumbered by the number of learnings that we had that we did not expect to happen. How did we get there? We got there by following a method, by trying to learn about things that we didn't know anything about, and by trying to learn each day something about why things did not work, and not just get excited about those things that worked. It took this many people, it took that many years. It started in 1993, almost from the first time that I arrived there in Heinz's laboratory at LBL before I had my own laboratory. I want to end my talk here with, again, remembering the person. Remembering the person that even though he's not here with us today, we carry a memory that I think will be with us forever. Those of you that had even less of a chance to meet Heinz Heinemann, the person, as opposed to Heinz Heinemann, the story, the history, the rock star of catalysis, okay? I think you missed out on a great opportunity, and I can sympathize with you because one of the great regrets is that I didn't come into his life earlier than I did, and that I got a much longer period of time to learn from him. There's something called immortality, okay? And for those of you who do not believe in certain types of immortality, we certainly have one here. And it is that it will be another 100 years from now, there will be a North American meeting, and there will be something that will be there as a result of Heinz Heinemann, and there will be a picture of him somewhere, and somebody that remembers, somebody who remembers someone who remembers Heinz Heinemann. I think that's how we outlive ourselves, and I cannot think of too many people that have done that better than Heinz. Thank you very much.
So I think we have a few minutes for questions from that very inspiring talk. So if you have a question, please go to the microphone.
May I?
Please.
My name is, Enrique Iglesia. I would like to ask you, how serious is the Koch deposition as far as the behavior of the membrane? This is a dream among the chemists, catalytic chemists, to make something out of methane, of use and value. And I wonder if you ever made a rough estimation of the economic feasibility study. At one time, since I was so skeptical with the data in hand, I made a private inquiry with 15 colleagues in Europe, and I got 9 skeptical answers and 1 positive answer. The 14 that said, said, I'm not against, I don't think it's impossible, but I wouldn't spend my time and my money on that. What is your feeling about the future and the possibility? Because if it's not economically feasible, that means it's no use for that. Thank you.
Well, so again, I'm the wrong person to talk about practical stuff. I'm an academic, and I do things because they're fun.
Yeah, but me too, but we have to keep in mind.
I know. So my view on the reason why we're not working actively in this area is not because the concept is not right. It's because the chemistry actually allows you only a very small range to operate with. If you don't remove, hydrogen, you have a thermodynamic problem. If you remove too much hydrogen, you acquire A goes to B goes to C goes to D, where D is not really what you want. So I think what we have done is drawn a box, okay? And that box looks like what we can do, what we know how to do, for people to now look at it. My personal feeling is that the benefit of this work is, again, the debris that we have left behind and not necessarily the fact that we can make amendments. My personal feeling, and it's a gut feeling more than anything else, is that this would be very difficult to implement economically in practice the way that I have envisioned it here.
But you remove the hydrogen, but the carbon is away from oxygen. It will stay there.
Well, it will stay there, but it stays there when I leave the hydrogen there too. So I'm not going to remove all the hydrogen from the system. I can tell you what not to turn and how much to turn, but I cannot avoid, I think, what is effectively a box within which we have to operate.
Thank you. So we have time for one more short question, if that exists. Okay, well, let's thank Enrique again for a very serious